Welcome to This Explainer. Today, we're tackling a massive roadblock in AI, and we're going to dive into a completely revolutionary protocol called LLM Semantic Compression, or LSC. Basically, this solves context window limitations for absolutely any large language model you might be working with. If you're building AI tools, you know firsthand that managing the sheer volume of information you feed into a model is one of the biggest bottlenecks out there. But what if we could compress that knowledge so effectively that the LLM processes it faster, cheaper, and with zero loss of semantic meaning? Well, let's explore exactly how this works.
Let's be real for a second. How many times have your prompts just completely failed because the LLM got distracted by fluff and ran out of memory? You're trying to feed it a decent-sized knowledge base, but the context window hits its absolute limit before the actual reasoning even starts. People in the industry call this the memory wall. But as we're going to see today, the real issue isn't necessarily the size of the context window itself. It's actually the inefficiency of human language. And the numbers behind this are just staggering. You can achieve a massive 60 to 65% token savings while retaining absolutely zero semantic loss. By applying the LSC protocol, you're slashing the size of your text by more than half. Imagine taking a huge 1,000-page technical manual and reducing its token footprint by almost 2/3, without losing a single technical requirement, version number, or logical rule. It sounds like magic, right? But it's really just highly optimized structural transcoding. To really understand why this is such a game changer, we have to look at why traditional retrieval-augmented generation, or RAG systems, struggle so much. These systems essentially just blindly dump raw verbose text right into your prompts. And what happens? Rapid context saturation. It multiplies your inference costs linearly, because you are paying for every single word. Plus, worst of all, it introduces all this cognitive noise. It confuses the AI with completely useless syntactic filler. I'm talking about articles like the and pronouns, and conversational pleasantries that carry exactly zero logical weight. So, what's the fix? It's LLM Semantic Compression. The LSC protocol strips away all that messy grammatical noise and transcodes your data into what is called a high-density logical format, or HDLF. Think of HDLF as this pure mathematical representation of your knowledge. It doesn't care about making sentences sound pretty or conversational for human ears. It literally only cares about preserving the exact logical relations, the constraints, and the entities present in the original text. This is where it gets really cool. When we look at standard natural language connectors, words like causes or defines, we can just replace them entirely with pure logical operators. Instead of writing out the word causes, HDLF uses a simple arrow operator to map the cause right to the effect. Instead of a clunky phrase like this variable is defined as, it just uses a double colon. We are replacing messy, ambiguous verbs with the super strict symbolic notation. This makes the reasoning vastly simpler, so much more linear, and significantly faster for the LLM to actually process. By feeding the model these clean mathematical operators instead of giant, wordy paragraphs, you are giving it absolute cognitive focus. Think about it. When an LLM doesn't have to waste computational power parsing through filler words and tangled grammar, its accuracy on multi-step logical inference tasks just skyrockets. It is literally like putting a pair of noise-canceling headphones on the AI. All the semantic distractions are gone, and only the pure, actionable logic remains. So how does this actually run? Well, it builds into this incredibly elegant four-phase pipeline called the JIT, or just-in-time architecture. First up, your raw documents are ingested and chunked. Second, they get compressed into those HDLF nodes. And here's the brilliant part. Your database rests permanently in that ultra-compressed state. Then, in phase 3, when a query is actually made, the system retrieves only the relevant compressed nodes. Finally, in phase 4, it expands them back out into natural language just in time for the user to read.
Let's look at a practical example. Compare a standard, super wordy server error to its HDLF counterpart. On one side, you've got this long human-readable sentence about a network error. On the other, a slick, purely logical chain. System arrow network error 404. Arrow cause server offline. I mean, it reads almost like code. It's incredibly dense, yet notice how it hasn't lost a single technical detail. The exact error code and the exact root cause are perfectly preserved.
And the math here really speaks for itself. In that server error example, the natural language sentence ate up about 35 tokens. The HLF compressed version? Just 14 tokens. You are slashing your token consumption by over 60% on that one single interaction. Now imagine scaling that across an entire enterprise knowledge base, or a really complex multi-turn autonomous agent workflow. The reduction in your API costs and processing time is absolutely massive.
Now, you might be thinking, okay, sure, this works for technical server logs, but what about everyday stuff? Not to worry. Even complex, culturally nuanced data like the Mediterranean diet is effortlessly mapped into a dense structural template. Natural language guidelines about eating plenty of fruit get translated into a strict logical rule. High consumption, defined as seasonal fruit, leading to a quota of greater than or equal to 5 portions a day. This totally proves the protocol works for absolutely any type of knowledge base, from software documentation to health guidelines. And because of this massive level of compression, you can effectively inject 3 times the amount of actual knowledge into the exact same context window. Take a second to really think about that. If your LLM has a limit of, say, 100,000 tokens, using HDLF means you are packing the equivalent of 300,000 tokens worth of raw facts, rules, and context right into that identical space. It completely pushes the boundaries of what any model can hold in its working memory at any given moment.
Okay, but a really important question. How do we prevent the AI from messing up or hallucinating during that compression phase? To maintain 100% semantic integrity, the protocol uses what's called an integrity contract. It strictly forbids the LLM from altering any numbers, technical keywords, or dates during encoding. They are treated as immutable constants. An HTTP 404 must remain a 404. A timeline of 5 minutes must stay 5 minutes. This strict guardrail guarantees 0 hallucinations.
Which brings us to a vital distinction. Unlike traditional recursive summarization, which slowly deletes vital details over time, that super frustrating phenomenon known as summarization drift, LSC uses structural transcoding. Summarizing basically says, hey, there was a network issue. Transcoding says, system, error 404. By mapping the structure rather than just shortening the sentences, LSC ensures your facts never drift or degrade, no matter how many times you process the data.
Ultimately, these mechanics unlock some pretty incredible efficiencies for whatever LLM you're using. First, by assigning unique hashes to logical nodes, you get global semantic deduplication. So if a rule appears in 100 different PDFs, it's only stored exactly once. Second, you achieve profound cognitive focus, letting the LLM reason over clean logic rather than messy syntax. And third, you're dropping your API inference costs by up to 65%, all while drastically cutting down the chance of hallucinations. It all leads us to this really incredible concept: creating a crystalline memory state for autonomous agents. By storing their long-term memory purely in HDLF, these agents can recall vast amounts of perfectly structured, immutable logic. So, if you can build autonomous systems with a crystalline memory, systems that never forget, never degrade, and never get confused by syntax, the real question isn't just how we're going to use them, but what limits of artificial intelligence are we going to break through next?